Hey, it's Dr. J. Finally going to finish chapter 5 today. So this will be our third edition of the zeros of polynomials. I've already given you all the theorems and techniques and such. This is really just wrapping it all up, making sure that you can factor and solve and find the zeros of polynomials. So let's just get going on it so we don't waste any time. So for this one, let's just find all the zeros. Zeros are also known as solutions to an equation. Really means the same thing. I think I mentioned that last time. So 2x cubed plus 9x squared minus 8x minus 6 is equal to 0. Okay, so now you can just start diving in, start throwing out numbers. I'm going to go ahead and make the list. So these are the possibilities. Now these are the rational zeros. So this list does not include any square roots or any imaginaries, which might show up later today. Now this is the P over Q list. So P is factors of 6, and Q is factors of 2. So we got plus or minus factors of 6, 1, 2, 3, and 6. And then we got factors of 2, which are just 1 and 2. So let's see how big this list is. 1 over 1, 1 over 2. 2 over 1, 2 over 2, but we already have that, so we'll skip it. 3 over 1, 3 over 2, and then 6 over 1, and 6 over 2, but 6 over 2 is 3, and we already have that. So we have 6 positive candidates and 6 negative candidates. You might try Descartes' rule, or Descartes' rules. If you look it up, it's called Descartes' rule, but there's actually 2 of them. So for the positive zeros, let's count the sign changes. We got none, 1, none. So you get 1 sign change. That's nice to know. That means there's 1 positive real zero. So for the negatives, it would be 2 negative x cubed, 9 negative x squared, negative 8 negative x, and then negative 6. And again, I think in the last edition I did this mentally, but in case you missed that, I'll just show you how to do it. So that would be negative 2x cubed, positive 9x squared, positive 9x, and then negative 6. So you have 1, none, 1. So you have 2 changes in f of negative x. I'll just say 2 changes. I don't have enough room to write that. So that means that there's 2 or none negative real zeros. Okay, and so that just gives us sort of an idea of what we expect to get. The nice thing about 1 sign change, you should be happy when that happens, that is a guarantee that there is 1 positive real zero. So that kind of tells you, well, maybe I should start with the positives. The negatives, there's either going to be 2 negatives or no negatives. Now, the chance of there being no negatives is pretty slim because the total degree is 3, and I haven't really discussed imaginary numbers yet, but that's what the no negatives means. It means that if you get an imaginary solution, imaginaries do not get counted in this process. This is only counting the real numbers. So I is not a real number. So that's what the 0 means. It means, well, there's a possibility that this has imaginary solutions. That's a possibility. But the likeliness, at least at this stage, until I get into imaginaries, is that there will be two negatives. All right. But although, if this was on a test or something, you'd still need to answer there are two or there's none, right? You still have to give me both possibilities. Okay, so let's get busy finding the solutions. So I'm going to set up my synthetic division here. 2, 9, -8, -6. Here's my list of candidates. I always start with 1. Let's see, so bring down the 2. 1 times 2 is 2. And then 11, and 11, and 3, and it looks like no. All right, so no, not a 0. I'm just going to save my little list here so I can keep that in mind as I'm doing it. Let's try this again. 2, 9, -8, and -6. So let's try 2. I usually try the whole numbers first, or the integers, and then I go to the fractions. If none of the whole numbers work or none of the integers work, then I usually go to fractions. So we're trying 2 next. So 2 times 2 is 4. That's 13. You can already tell it's not working. 26. What do we got? 26 and -8 is, what's that, 18? 2 and 18 is 36. And the remainder is 30. So now I'm just going to make a comment, okay? And this is not a theorem that I'm going to necessarily test you on, but it will sort of subliminally be in there if you notice it. And so this is a corollary. I always forget how to spell corollary, but whatever. Sort of like a side theorem to Descartes. If all of the values in the quotient and the remainder are positive. In fact, they don't even have to be positive. They just have to be not negative. So for example, one of these could be 0, and that would be okay. But if all of these values are not negative, then the divisor, in this case 2, is an upper bound. In other words, no zeros will be found beyond that point. That's what an upper bound is. It's saying that it's like a fence, and no answer is going to be found on the other side of that fence. All right, which is very important because I was about to try 3, and then I was about to try 6. Right? But I know that they're not going to work. Yeah, so I'm not going to waste my time trying 3 and 6. If you want to waste your time, you can. But if you remember the corollary, it's called the upper bound corollary. Some people call it the upper bound theorem, but it's really just a corollary. If you want to know intuitively how it works, think about it. If your quotient and remainder are all non-negative, that means there are no sign changes. So Descartes' rule of signs, if there are no sign changes, that means that you're going to get no zeros because there are no sign changes in this result. So that's kind of intuitively how this works. It's really just an extension of the rule of signs. All right, so that saves me a little bit of time. I'm not going to try 3 or 6. So now I have a choice. I can either keep trying positive numbers. I only have 2 fractions, so I could give them a try. Or I could switch over to the negatives. It's really up to you. Okay. Maybe I'll give one of these fractions a try. Let's try a half. So we got 2 times a half is 1. 9 plus 1 is 10. A half times 10 is 5. Negative 8 and 5 is negative 3. Nah, look. A half times negative 3 is negative 3 halves. I'm just going to say not 0. I'm not going to spend a bunch of time trying to calculate that because I know that it's not 0. All right. Let's try 3 halves. I'm going to try to double dip here and reuse this one. So I got 3 halves times 2, that's 3. Remember, 3 halves is just 1.5. I never write it that way. I always write 3 halves, but you could certainly just write that as 1.5. 9 and 3 is 12. 3 halves times 12 is 18. Right? 3 times 12 is 36, and then 36 divided by 2 is 18. Negative 8 and 18 is 10. 3 halves times 10 is 15. And so my remainder is 9. So it's again not 0. All right. So I'm done. I'm done. I've tried everything. I tried 1, it didn't work. I tried 2, and it told me that it was an upper bound. So I'm not going to bother trying 3 or 6. I tried 1 half and 3 halves. I have exhausted my list. Oh, shoot. I don't know why I erased it, though. So now my list is only negatives. 1, negative a half, negative 2, negative 3, negative 3 halves, and negative 6. So now I have a smaller list. So now I'm going to try some negative numbers. I'm not going to try any more positives. Now you might be thinking in the back of your head, well, wait a minute. Descartes' rule said there was going to be one positive 0. How come none of these worked? So I'll just make a little note. If no positive rationals work, and when I say work, I mean, give you a 0 remainder, then, and Descartes' rule predicted at least one positive real 0, then it must be irrational. I don't know if you can see that. All right. It's very difficult to see, isn't it? So there's the theory. There's my little note down here. It's not a very important note. It's just a way of predicting what's going to happen, right? So I know now, because Descartes' rule said there's going to be a positive 0. I tried all the positives that were rational, although some of them I didn't try. I didn't try 6. I didn't try 3. But the theorem still is true. It just tells me that the positive real 0 must be irrational. I don't know if you can see the word irrational. And so now I already know what I'm going to get. Okay, I know that I'm going to get an irrational number. I know, I'm talking forever. I should probably just solve this thing. So let's go through our list of negatives and see what we get. Negative 1 times 2 is negative 2. 9 and negative 2 is 7. Negative 1 and 7 is negative 7. You can already tell it's not going to work. Negative 1 and 15 is 15, and then 9. So again, it's not 0. I'm going to do all the integers first. So negative 2 times 2 is negative 4. Then I get 5. and I get negative 10, I get negative 18, I get 36, and I get 30. Again, it's not 0. This is where having some intuition might help, right? You might have a spirit or a feeling or a thought or something that tells you which one of these you think is going to work. I don't know if you can see them all. There's a negative 6 over there. So I've had students that go, hey, I'm just going to jump right to negative 6 and give it a try. What the heck? You know, maybe you got a feeling about it. Negative 6 times 2 is negative 12. 9 and negative 12 is negative 3. Negative 6 and negative 3 is 18. That's 10. Oh, no. Sometimes feelings are just feelings, and they don't really mean anything. All right, so what have I tried? I tried 1, I tried negative 1, negative 2, negative 6. My last hope for an integer solution is negative 3. You're my only hope. Negative 3 times 2 is negative 6. 9 and negative 6 is 3. That's negative 9. Nope, not looking good. No. That will happen at least once in the homework, where you try every integer, every whole number, every negative integer, and none of them work. You just got to try some fractions once in a while. All right, so let's try negative a half. So negative a half times 2 would be negative 1. And then that would be 8. That would be negative 4. Negative 12. There it is. Winner, winner, chicken dinner. Okay. So we got one. Cool. So we got a 0, or a solution. X is equal to negative a half. I didn't ask you to factor this one, so I'm not going to bother putting it in factor form, but that would be a separate exercise there. Okay, so we're done now. Now we can take this out. Now it's quadratic. So it's 2x squared plus 8x minus 12. And of course, we're looking for zeros, so set that equal to 0. Now, the first thing you should do when you have a quadratic equation is to try to factor it. All right, so look for something they have in common. Looks like they're all even. They're all divisible by 2, so you can factor out a 2. All right. Now, I mentioned this back when we were doing the quadratic equations. This is a constant, all right? If I were doing the complete factorization, I would have to hang on to this constant. So I sometimes refer to that as a little brother. You can forget about them, you can drop them off, but you better remember to go back and pick them up. In this example, I'm only asking for the zeros. So that means that you can divide both sides by that constant, and you never have to go back and pick it up. All right, but I'll put a little note here. Let me put where you can read it. Note, if you are factoring, in other words, complete factorization, you got to go back and keep this constant. All right. In other words, put it off to the side. You know that one of your factors is 2. And so when you present your final answer, you'll have to make sure that that 2 is included. All right, so now you have some choices here. You can either solve by factoring, continue to factor if possible, or you can use completing the square, or you can use the quadratic formula. All right, I always try factoring first. So just give this a good try and see if it's possible. All right, try to find 2 numbers that multiply to be -6. a little bit difficult to see there. Try to find two numbers that multiply to be -6. So you could try maybe 3 and 2, but they don't add to be 4. So it's impossible to get a 2 and a 3. You can get them to multiply, right? You can go, +2, -3. That multiplies to be -6. But it doesn't add to be 4. Or you could try -2 and +3, and again, that multiplies to be -6, but it doesn't add to be 4. So that's not going to work. You could try 6 and 1, but again, the same thing happens. No matter how you put the signs, you're never going to get -4. So it is not possible to factor this one. All right, so now you can either do completing the square or the quadratic formula. Remember way back when we learned this, I think it was it chapter 2 or something? My suggestion was if the middle number is even, the b is even, then completing the square is very simple. It's much easier than the quadratic formula. But again, that's a personal choice. I'll leave it to you to do that. So we're going to add 6 to both sides. Leave a blank spot here. Remember the process. This is a nice review. Half of 4 is 2. 2 squared is 4. So the magic number is 4. If it's been a while, we could review completing the square. You take half of the middle number. Half of 4 is 2, and then you square it. And it goes back to being 4. And then you add this number to both sides. So that's a quick little review of completing the square. Very quick. Okay. Remember, when you do the completing the square, you automatically get a perfect square. That's the whole point. So you have x plus 2 squared is 10. All right. And now you're going to take the square root of both sides. Don't forget the plus or minus on the right-hand side. So now you have x plus 2. Remember, these guys are going to cancel out. You could drop the parentheses now. Is plus or minus the square root of 10. All right. See how much easier that was than the quadratic formula? You could have used the quadratic. You would get the same result, but it takes a little bit longer. You're going to subtract 2 from both sides or add -2. It means the same thing. Remember, you're going to put it right in front of the plus or minus, and there you go. So those are your real zeros. They are real. It means they exist on the number line, but they are irrational. So if you wanted to know what they actually are, you'd have to use a calculator. The square root of 10 is about 3 point something, a little bit more than 3. I say 3.1. If you're really curious, you can grab your calculator. Square root of 10 is 3.16. Yeah, so this would be approximately -2 plus or minus 3.16. Which would be, -2 plus 3.16 or -2 minus 3.16. So you get, I don't know, what's that? 1.6 or -5.16, sorry. 1.16 or -5.16. This is just if you're curious about where it is. What are these values on the number line? Yeah. I typically don't ask for this unless it's a specific approximation problem. Maybe we're doing a word problem or we're doing something where we really want to know the value. Typically, I like the exact values. All right. And this caused a lot of problems in some of the earlier chapters because, all throughout your life, you probably think of a calculator as being exact, right? I've had students tell me, really? A calculator is not exact? Well, no, it's not. A calculator, when we're talking about square roots of irrational numbers, They always give you approximate numbers. Okay, so what are the real zeros? The real zeros, remember, we already had one, which was -0.5. We also have -2 minus the square root of 10. And then -2 plus the square root of 10. So altogether, you have 3 real zeros. And if you think of the rule of signs that we talked about, Descartes' rule of signs, we have 2 negatives and 1 positive. Yeah. So Descartes was right. So Descartes' rule predicted that we would get 2 negatives and 1 positive using the rule of signs. So it's exactly right. I hope it's clear that these are both negative numbers. Yeah, these are both negative numbers. Remember, this one is the same as this, -5.16. It might not be obvious that this is a positive number, but when you put it into your calculator, you see that it's actually positive. Yeah, -2 plus the square root of 10 is actually positive. Okay, if I were to ask you to factor this polynomial, you'd have to go back and put it back together with the parentheses in factored form. I'm going to do plenty of that in the next few examples moving forward, so I'm going to go ahead and end this one and move on to the next example. Factor completely. F of x is x to the 4th minus 2x cubed plus 9x squared minus 16x plus 8. All right, so the plus or minus p over q are just going to be factors of 8. Nice, yeah, because the q is 1. So if you really want to be, super precise, it's 1 over 1, 2 over 1, 4 over 1, 8 over 1, and nobody ever writes that. So it's really just plus or minus p, right, because the q is 1. All right, so that's 8 possibilities. If you want to use Descartes' rule, I don't know if it really helps in this case, but we could do it really quickly. I won't write it down. I'll just talk my way through it. 1, 2, 3, 4. Well, I said I wouldn't write it down. So 4 or 2 or none positive zeros. You can't see the none, huh? 4 or 2 or none positive zeros. I've got this little space here that you can't see. So 4 or 2 or none. All right. That's not very useful, is it? When this happens, Descartes' rule doesn't really help you very much. Well, there could be 4, or there could be 2, or there could be none. It doesn't really help very much. Let's see if the negative works. I said I wasn't going to write it down. I just can't stop myself. So for the negative, it would be x to the 4th plus 2x to the 3rd. Plus 9x squared plus 16x plus 8. Oh, that helps. Yeah. No sign changes. No negative zeros. That is very helpful. Now I'm glad I did it. I was about to start trying negative numbers. And so now this list is much smaller. And again, these are the possible rational zeros. Whole numbers are included in rational. Yeah, they are rational. They're ratios, 1 to 1, 2 to 1, 4 to 1, 8 to 1. Those are ratios, rational numbers. That's really cool, right? I was literally about to waste 5, maybe 10 minutes trying these negatives, the plus or minus here. And now I know if there's no negatives, I can omit the negatives and only try the positives. Okay, so let's get busy. So we've got 1, -2, 9. Look for missing terms. No missing terms. -16 and 8. And let's start dividing. So here's my possibilities. I'll probably have to erase this at some point. Let's try 1. I always start with 1. 1 times 1 is 1. -2 and 1 is -1. 1 and -1 is -1. 9 and -1 is 8. 1 times 8 is 8. -16 and 8 is -8. Looking pretty good. 1 times -8 is -8, and there it is. Yeah. We got one. That's why I always start with 1. I used to think, oh, I'm not going to, there's no way, right? There's no way 1's going to work. And so I would skip to other numbers, then sure enough, 1 would work. It's a little bit of a, give and take. It's not going to work every time, but it's so easy, you might as well try it. And then remember, if you get a 0, you don't have to start over. In fact, don't start over. You'll end up running around in circles and never get out of this thing. Try another candidate. So let's try 2. 1 times 2 is 2. -1 and 2 is 1. 1 times 2 is 2. 8 and 2 is 10. 2 times 10 is 20, and it does not look good. Right. But remember, these are now all non-negative. So 2 is an upper bound. So don't try 4 or 8. Remember, my list was 1, 2, 4, and 8. But look, those are all non-negative. So if I keep trying, I could try 4, I could try 8, and I already know it's not going to work. All right. Again, this is like a polynomial, x to the third plus x squared plus 10x. Actually, no, it's x squared plus x plus 10 plus 12 over x plus 2. And so those have no sign changes. Yeah. So they can't possibly have any solutions. All right. So if that happens, go back to here and try 1 again. Now, I never know if the same number is going to work more than once. Some people just have a strategy that says, well, if a number works once, try it a second time. It might work a second time. That is certainly an option. It's actually not a bad idea. I never think to do that. So the way I do it is I just try every single number, and then if none of them work, or if I have some reason to not try them, some theorem that tells me don't do it, then go back and try one of these numbers again. So bring down the 1. 1 times 1 is 1. That's 0, 0, 8, 8, and what do you know? It works again. So x equals 1 is a 0 of multiplicity 2. All right, the same value worked twice. And now I have a quadratic. 1x squared plus 0x plus 8. I'm just going to write it the traditional way. X squared plus 8 equals 0. I was hoping for, I guess we're going to get imaginaries. Yeah. So x squared plus 8 equals 0. I'm checking for mistakes because I was not expecting imaginaries this early in the lecture. Well, I guess we got them. Unless there's a mistake, I'll leave that to you to find one if there is one, but I didn't expect this to happen. So x squared plus 8, how do you solve this? You move the 8 to the other side, and you get x squared equals negative 8. X squared equals negative 8. And now, I don't usually use the quadratic formula on these very simple ones. If there was a middle term that was not 0, I'd probably use the formula. But this doesn't have a middle term, so I'm just going to use the square root. Don't forget there are 2 possible square roots. So that is plus or minus. Well, let me break this up. We haven't done imaginary numbers in a while, so maybe I'll just put it up here. Plus or minus the square root of negative 8 is plus or minus the square root of negative 1, the square root of 4, and the square root of 2. So I just break down the 8. I was hoping it would be like 9 or something like that, but it's not. If it's 9 or 16 or 25 or something, you get a much nicer answer. But this is not going to be the best, but it is what it is. Square root of negative 1 is I. Square root of 4 is 2. And then the square root of 2. And we usually rewrite it like this. 2i square root 2. All right. Okay. I don't see any sign errors, so I guess I'll wrap this up. I'm a little suspicious because it's not what I expected, but you know, you don't always get what you expect. Yeah, that is what it is. Okay, so our final answer is the complete factorization. So the zeros are 1, 2i square root of 2, and negative 2i square root of 2. But 1 has multiplicity 2. So when you do the factors, you're going to go x minus 1 squared because it has multiplicity 2. And then the imaginaries are just going to be x minus 2i square root of 2 and x plus 2i square root of 2. So the one that's positive, when you put it in, it's negative. And then the one that's negative, when you put it into the factor, becomes positive. And so that is your complete factorization. And I guess, you know, I'm now going to start talking about imaginary numbers because they just showed up to the party. So example 3. This is actually a review problem from, I don't know, long time ago. Beginning of chapter 3, I think we did this, right? I think so. Imaginary numbers. I think that was chapter 3. Now, I kind of already spoiled it. I told you that this is going to have imaginary numbers, but I mean, suppose you didn't know that. Well, you would look at it, and it has no sign changes. Yeah. So you know it has no positive zeros. And then when you do the negative rule, you end up with 2 sign changes with the negatives. If you don't believe me, watch. This one will be x squared. That one will change to negative 2x. And then that one will stay positive 5. So we'll have 2 sign changes, which means it either has 2 or none positive zeros. So, negatives. So positive zeros, none. Right? In other words, 0. negative zeros, 2 or none. Yeah. Well, in this case, it's none and none. This is exactly the case where there actually are no positive zeros and no negative zeros. Imaginary numbers, also known as complex numbers, are neither positive nor negative, which is not intuitive, because when you say, 2 plus I, that looks positive to me, Negative 2 plus I, that looks negative to me, but they're not. The idea of positive and negative come from basic arithmetic and the number line. These numbers do not live on the number line. They don't have a place on the x-axis. And so they can't be positive or negative because that's what positive or negative mean. Positive if you live on the right side of town, negative if you live on the left side of town, right? It's a sort of a geographic location on the line. Well, these don't live on the line, so they are neither. Now, I don't know if these are the answers, but this is the kind of thing that you're going to get. Let's go ahead and solve it. I'm just going to, why don't I use completing the square? That's a nice technique. I like completing the square. So x squared plus 2x equals negative 5, just to show you don't always have to use the quadratic formula. If you remember, the middle term is even and the leading term, leading coefficient is 1, then that's a perfect candidate for completing the square. So half of 2 is 1, 1 squared is 1, so I'm going to add 1 to both sides. Then I'm going to factor this. So x squared plus 2x plus 1 factors, x plus 1 squared. And I'm going to combine this to negative 4. Then I'm going to take the square root of both sides. Don't forget the plus or minus. Ah, this is nice. I love it when that happens. If the radicand is a perfect square negative, so negative 4 is a perfect square negative, then that's going to be 2i, right? If it's 4. If it's 9, it would be 3i. 16 would be 4i, and you know all your square roots. So, and then don't forget the plus or minus. Bring the negative 1 over and put it in front of the plus or minus. And there's your solutions. On the homework, you have to type them out separately with a comma between them. So that's typically how I would list the solutions. All right. So let's get into it. Let's do another one. Example 4. This is a really interesting problem, I think, from a sort of philosophical standpoint. And like, how do you feel? What do you believe about numbers? What do you believe that they behave? How do you believe? I don't know about you, but when I go to solve this equation, watch. You move the 1 over. Now, be careful. This is a cube, not a square. So you take the cube root of both sides, not the square root. And the cube root does not have a plus or minus. There's no such thing as plus or minus the cube root. There is just the cube root. That's it. There's only one cube root. So the cube root of negative 1 is, again, not an I because it's a cube root. It's just negative 1. Yeah? The cube root of negative 1 is just negative 1, right? Because negative times a negative times a negative, right, 3 negatives, just goes back to being negative 1. So it seems that there is only one solution. But there's not. There are 2 more. You got to use synthetic division. So you're going to take your polynomial, your original polynomial, and you're going to put it inside the synthetic division. All right, and I'm talking about the original, x cubed plus 1, before I started messing with it. So that's 1x cubed, 0x squared, 0 x's, and then a 1. And I know that negative 1 is a solution. So I already know that I'm going to get 0 for a remainder. I already know that, right? Because I already know that it's a solution. And remember, if you are a solution, then that means you are a 0. If you are a 0, that means you are a factor. And if you are a factor, that means that your remainder is 0, right? It's a chain of implications, right, that are all connected together. Nothing is an island, right? I mean, everything has a bridge connected to something else. I guess it could be an island with a bridge, but yeah. Negative 1 times 1 is negative 1. 0 and negative 1 is negative 1. Negative 1 and negative 1 is 1. And then 0 and 1 is 1. Negative times a positive is a negative 1. And there it is. Check, exactly as we expected to get. And now we can take this guy out and use the quadratic formula. Now this time, since the middle term is odd, I'm going to go ahead and stick with the quadratic formula. So I got x is negative 1 plus or minus the square root of negative 1 squared minus 4 times 1 times 1 all over 2 times 1. So that's 1 plus or minus the square root of negative 3 over 2, which is 1 plus or minus I square root 3 over 2. Unfortunately, 3 is not perfect, so it's stuck inside, but the negative can come out like a negative 1. So just treat the negative as if it were a negative 1, and when you take a negative 1 outside of the radical, it becomes I. Now this is a square root, as opposed to this is a cube root. And so these are sometimes called the third roots of unity. Why unity? Uno, yeah, 1. So these are the 3 roots of negative 1. Yeah. I guess it's negative rooted. Negative unity, yeah. The roots of negative 1. You can do a similar process for positive 1 if you like. So what are they? Negative 1, that was my original one over here. And then these two guys down here. Now those are not very easy. They don't simplify very nicely, so you just put them in like fractions. And there you go. Those are your third roots of negative unity. Okay, most of the next few examples that I have time for are, I have to finish this, so we're not going to part 4, are all going to be cubics, right? They're not going to be quite as simple as this one, though. But the basic idea with a cubic is you get one real number and then you get 2 imaginary numbers. Typically, I mean, in this particular presentation that I'm giving. So. In the real world, you never know what's going to happen. I mean, anything could happen. All right, so let's find all the zeros of, I'm just getting tired of calling every function f, so I'm going to call this one g. And so that'll be x to the third plus 13x minus 116. 116. There are a lot of possibilities. You want to maybe take out your calculator. The factors of 116 are 1, 2, not 3, but 4, not 5, but 6 maybe? No, not 6. 8. Nope. 29. 116 divided by 4 is 29. And I guess it's not as many as I thought. What's 116 divided by 2 is 58. And then 116 itself. So it's not quite as many as I thought. When I first saw that number, I thought, oh, shoot, I'm going to have dozens and dozens of possibilities. But it's only 1, 2, 3, 4, 5, 6, and then 12. So 6 positives and 6 negatives. I've already kind of exhausted the theorems of Descartes and such. At this point, I'm just going to start diving in. If you have a feeling, go for it. You know, you might feel, oh, 29 that's my lucky number. You know, it's coming to me. I'm going to go ahead and try that. But I'm just going to go with 1 like I always do. So I start with 1. There is only one sign change, by the way. So there's a missing x squared. So put a 0 there. And get busy, right? By the way, I don't think it's going to work. How am I ever going to get to 116 with 1? So I could just quit now, but let me show you. 1, 1, 1, 14. No way. It's just not going to happen. So 1 doesn't work. I didn't think it would, right? You got a feeling? Let's try 29. Like I said, maybe 29 does work. Let's see. 1 times 29 is 29. That's 29. Oh, no, it's way too big. Yeah, look what happens. 29 times 29 is 841. No way. Yeah. Once you blow up to, big number, the chances of it shrinking back down to 0 in 2 steps are just so small. It's not going to happen. So, sorry, 29. You're not happening today. Let's try 4. This is the bounce around technique. Just try everything. 1 times 4 is 4. 4 times 4 is 16. 29. There's that 29. 4 times 29 is 116, and there it is. We got it. Okay. So we got one of the zeros. X equals 4. We'll save that for later. Now, I don't need to keep dividing. I've got 3 terms, so that's quadratic. Either use completing the square or the quadratic formula. I like completing the square. I think I've said that a lot. So I'm going to move the 29 over. Half of 4 is 2. 2 squared is 4. So I'm going to add 4 to both sides. Then I factor this. X plus 2 squared. Negative 29 plus 4 is negative 25. Take the square root of both sides. X plus 2 is plus or minus 5i. I love it when that happens. I made it so this happens quite a bit. It's not going to happen every time, but quite a bit you get perfect squares. And then move the 2 over, minus 2, minus 2. Remember to put it in front here. And so your zeros are x equals 4 and x equals negative 2 plus or minus 5i. And again, on the homework, you're going to put 1 real, and then 2 imaginary. And that's how you would write the answer. Let's try another one of these. Let's try another one of these. Factor completely. F of x, I'm back to my old f of x function. Oh, man. Come on. Well, we'll give it a second. We'll see if it comes back to me. X to the third minus 3x squared plus 7x plus 75. Oh, good. Came back to me. I didn't even have to yell at it. All right. So, what are my possibilities? Let's just make a little list over here. Possibilities are factors of 75. So 1, 5. How about 3? 75 divided by 3? Yeah. 1, 3, 5. How about 15? 75 divided by 15. Yeah, 15. 25 and 75. One, 3, 5, 15, 25, and 75. Hopefully, when you're doing this on your quiz or on your test, you can just make the list mentally, at least. That's what I mean by this, so that you know what you're going to be trying. So don't try 10, don't try 2. That's mainly what this list is for. It's telling you what not to try. Don't try any number that's not one of these numbers, right? All right, let's dig right in and go for it. Maybe we'll get lucky. 1, -3. You only got to get lucky once. That's what they say anyway. All right, so again, I always try 1 even if I know it's not going to work. I don't have a lot of hope that it's going to work because look at how big this number is. Right? And think about how this process works. It's kind of a growing process through multiplying and adding. So you think that you're going to grow this to be 1? I don't think so, but let's give it a try anyway. No, I didn't think so. Let's try 3. I don't really have a strategy at this point. Just try everything. 3 times 1, and then 0, and then 3. Oh, nope, not 3. 3, 0, 0. Oh, God, I hope I didn't make that mistake earlier. 7 and 0 is 7, and 21. I'm almost there, but not quite. Nope. Let's try 5. 5, 2, 10, 17. No. Not going to work. And not only that, but look at, they're all positive. I'm not going to bother with 15, 25, or 75. Yeah. 5 times 17, I think, is 85. And so you end up with like 160 or something. Yeah. So these are all non-negative, which means 5 is an upper bound. You're not going to find anything beyond 5. So stop looking. Stop looking. Let's start doing negatives. Let's try -5. What the heck? I might as well just jump right to it. -5 and 1 is -5, and then that'll be -8. That'll be 40. That'll be 47. No, I can already tell. That's going to be negative 235, and that's definitely a big no. Right? And this is completely acceptable. If once you see that it's not going to happen, you can stop wasting your time with it. Let's try negative 3. Negative 3 times 1, negative 3. That'll be negative 6. That'll be 18. That'll be 25. There it is. Winner, winner. Hey, we got it. Okay, let's just put this off to the side. The factor is x plus 3, just so we don't forget. All right, the problem is telling us to factor, so we got the factor is x plus 3. Pull this out, so we get 1x squared minus 6x plus 25 equals 0. A lot of people forget the equals 0 part. It's wrong if you do that, but it actually is forgivable. You will still get the right answer if you don't do the equals 0. I'm going to do the equals 0 because I'm a mathematician and I'm bound by an oath to do it correctly. So minus 25, minus 25. I don't want to lose my membership. When somebody watches this and says, oh, we're kicking you out of the club. All right. So half of 6 is 3. 3 squared is 9. So I'm going to add 9 to both sides. A good variety today, right? A lot of variety today. I know sometimes my lectures lack variety. It seems like I do the same problem over and over again, but I mean, each one of these is coming out different. That's negative 16. Love it. Negative 16 is going to be a perfect square. Yeah. So I get x minus 3 is plus or minus the square root of negative 16. So I get x is 3 plus or minus 4i. Right? The 16 becomes the 4i, yeah? And then when you move the 3 to the other side, it's a negative 3, but when I move it over the equal sign, which is, again, why the equal sign is important. If you leave off this equal sign, it can really cause problems, so you end up with a positive 3 there. Okay, and so my factors are x plus 3. That's this one. And then these two. Now you got to be careful with the imaginaries. It's x minus 3 minus 4i and x minus 3 plus 4i. They originally start with minuses, always. So your imaginary solutions always begin, when you write them as factors, they always begin as negatives. Now, once you simplify, some of them might change. I do want you to simplify as much as possible. So this 4i changes to positive, and then this one changes to negative. Now, if you already calculated that mentally, then you could just jump right to here, and there's your answer. Okay. So again, these are zeros. Negative 3 and 3 plus or minus 4 are the zeros. Then the factors are up here. All right. One more? Yeah, one more. This next one's a real beast, so I give you a good hint to get you started. Okay, I warned you about this one. This will be the last example. Find all the zeros of this polynomial, given that 2i is a 0. Now, if this were not the last example of Chapter 5, I had more time, or we were, exploring complex numbers a little deeper, I would tell you a little bit more about what I'm about to say. But for the purposes of this course and the purposes of, the quiz or the test or whatever, you just need to know this fun fact. And I don't need to go into all the theoretical details about why it's true. Complex, also known as imaginary, solutions, also known as zeros, always occur in pairs. You can't have one without the other. So if I is a solution, then negative I is also a solution. If 2i is a solution, then negative 2i is a solution. If 3i is a solution, then negative 3i is a solution, etc., etc., etc. So when I give you this type of a problem, usually this happens with the very large ones, that if they have imaginary numbers and they're bigger than, say, third degree, I typically give you a hint. And so even though I'm only giving you one hint, I'm actually giving you two hints. So x equals 2i is a 0, and x equals negative 2i is a 0. I've got my pair, peanut butter and jelly, salt and pepper, yes and no, on and off, up and down, left and right. Everything has sort of an opposite in the spectrum of complex numbers. Okay, so just use that fun fact. If I give you one, I actually have given you two. Now we have to take this a little bit further. If 2i is a 0, then that means x minus 2i is a factor. And if negative 2i is a 0, then the opposite, x plus 2i, is a factor. Yeah. So by the factor theorem, the remainder, when f of x, that's our original polynomial, is divided by x minus 2i and x plus 2i, must be 0. Yeah, that's the factor theorem. Now that is a theorem that you need to know. Hopefully you already know it, right? If you have a factor, then you have a remainder of 0, right? It must be true. Okay. So let's multiply this out. We get x squared plus 2ix minus 2ix minus 4i squared. This always happens with conjugate pairs. That's what these are called. The pairs are called conjugates. And so whenever you have conjugates, the center, the middle terms always cancel out. If you're really good at this, you can just skip that step because you know that those are going to cancel, and you can just jump right to this step. So you have x squared minus 4i squared. And remember what I squared is. I squared is negative 1. Reviewing chapter 3, I think it's 3.1, where we learned about the imaginary numbers. And so this becomes x squared plus 4. Now, how does that help us? Well, that means that if we divide by x squared plus 4, we know the remainder will be equal to 0. So I'm not guessing, I'm not hoping, I am 100% confident, as long as I don't make a mistake, that this will come out to have a remainder of 0. Now, unfortunately, because this is x squared, you can't use synthetic division. So I've broken out my old school long division symbol, and I'm going to do it the old-fashioned way. All right, here we go. Wish me luck. X squared goes into 5x to the 5th. 5x cubed times. Multiply, you get 5x to the 5th plus 20x to the 3rd. Here comes the negative. Change that sign, kill the leader, and start another cycle. Call that a revolution. Now you're going around the cycle one time. 17x to the 4th comes down. We get 13x to the 3rd. Bring down everybody. I don't want to forget those terms. 53x squared, 52x, and negative 60, and start the cycle over again. So x squared, 17x to the 4th, that'll be 17x squared. Multiply. 17 times 4 is 68. That's not one you typically memorize, but if you have to, use your calculator. Subtract, kill the leader, and then repeat the process. 13x cubed minus 15x squared plus 52x minus 60. And start again. So x squared, 13x cubed, that'll be 13x. 13x times x squared is 13x cubed. 13x times 4 is 52x. That's a 13 up there in case it's not clear. Here comes the negative, starting another revolution, kill the leader, bring down the remainder, which eventually will be 0. Oh, look, that's always fun. You not only kill the leading term, but you kill one of the following terms as well. We know we're almost done, and we know we're going to get 0 remainder. So this is negative 15x squared, so this must be negative 15. Negative 15 times x squared is negative 15x squared, and it's no coincidence. We knew this would happen. Negative 15 times 4 is negative 60, and when you go to cancel, you kill the leader and the remainder, and there it is, remainder of 0, as expected. Remember, in the early days of this, we never knew what was going to happen. But if you have a theorem, or maybe a couple theorems to help guide you, then you already know what's going to happen. All right, now we are by no means done. We just have taken a large, what's called a quintic, that's a 5th degree polynomial, and we've broken it down into a 2nd degree, which we've already solved. I'm just going to write plus or minus 2i, and I'm going to save that for later. And now I'm going to erase all of this, and I'm now going to say q of x, that's our quotient, is much smaller now. It's a cubic. And in the homework, there's tons of cubics. So if you can solve this cubic, you can solve any cubic. So let's go ahead and solve 3 more zeros. In general, whatever the exponent is, that's how many solutions you expect to get. Okay. Let's see. We got 5. Now we can use synthetic division. 17, 13, and negative 15. Going back to synthetic. My possible factors are factors of 15 divided by 5. So these are my candidates. So 1, 3, 5, 15 divided by 1 and 5. In other words, I'm only going to try numbers that appear in this list. 1, 1/5, 3, 3/5, 5, 5/5, but 5/5 is just 1, and 15, 15 over 1, and then 15/5, but that's just 3. So here are my candidates. Okay. All right. I guess I could do Descartes' rule really quickly. There's one sign change. Yeah, one change. So that means there's one positive 0. That's nice. I like it when that happens because that's a guarantee. So let's go ahead and take one of these positive numbers. I'm not going to start with negatives. I'll start with positives. If there were no positives, then I would just do negatives as my candidates. We've seen that before. You know me, I always start with 1. 1 times 5 is 5. That's 22. That's also 22. 13 and 22 is 35. 1 times 35 is 35. Remainder 20. Yeah. These are all non-negative. So that means 1 is an upper bound. It's always whatever you divided by, that's your upper bound. So don't go looking past 1. Isn't that cool? That means we're not going to try 3. We're not going to try 5. We're not going to try 15. Right? I'm only trying positives right now. And I'm also not going to try 1 because I know it doesn't work. So now my list of candidates is down to just 2 possibilities. 1/5 or 3/5. So next time I do this, (5, 17, 13, negative 15), I'm only going to try one of these fractions. Let's try 3/5. And it really is a 50-50 chance. If I try 3/5 and it doesn't work, then I know it's got to be 1/5, right? And if I try 1/5 and that doesn't work, then I know it has to be the other one. 3/5 times 5 is 3. 17 and 3 is 20. 3/5 times 20 is 12. 13 and 12 is 25. 3/5 and 25 is 15. And there it is. We got it. Now, I don't know how many attempts it will take the average student to do it. It might take you 2 or 3 tries. It might take you 10 tries. But if you try every single candidate, eventually you're going to get one. Now we can take this out. Oh, I don't have to keep going. I can take it out. 5x squared plus 20x plus 25 equals 0. And I can solve it by any method that I like. I can use quadratic formula. I can use completing the square, whatever you like. You might notice that these are all divisible by 5. So we could divide everybody by 5. It's another factoring technique. It means the same thing as factoring out of 5. And I feel like we've seen this type of problem before. Let's use completing the square. So I'm going to move the 5 onto the other side. All right. I'm going to complete the square with half of the middle term squared. So half of 4 is 2. 2 squared is 4 again. 4 is the most perfect of all perfect squares. And so now I have x plus 2 squared is equal to negative 1. I'm saving that. So now I've got x plus 2 squared is -1. And if you prefer the quadratic formula, go right ahead. You'll get the same answer. Take the square root of both sides. X plus 2 is plus or minus the square root of -1, which is plus or minus I. And we're done. Move the 2 to the other side. And there you go. They're sort of a distant cousin or a relative of the other two imaginaries. So these two come in pairs, and these two come in pairs. So you got salt and pepper, and you got peanut butter and jelly. You got 2 pairs of pairs. Yeah. Or you have a pair of pairs. And don't forget that you have one rational solution as well. So finally, the answer is the zeros are, I usually put the rational one first, although it doesn't really matter. 3/5, and then the other two, 2i and -2i. Those were kind of the freebies. I gave you those as a hint. And then you got these ones, -2 plus I and -2 minus I. And that's about as bad or as good as it gets, depending on how you look at your mathematics education. There is a section 5.6 in the book, but we're not going to cover it this semester. We've already covered a lot of the stuff that's in it, and we're getting, pretty far along here, and the test already has enough questions, so I don't need to add any more. So your test is coming very soon. Check on Canvas for all the due dates and announcements. And until we see each other again, this is Dr. Jordan. I'll see you on the internet.